Hello guys, so welcome back to another chapter in AC motor control methods. Today we're going to talk about motor and starting methods. We're going to talk about the most important factors to consider when selecting motor starting equipment. We're going to talk about why reduced current starting is important. We're going to describe several typical starting methods. We're going to talk about squirrel cage induction motors. And we're going to talk about how to identify or how to describe squirrel cage motor functions. There are two reasons for the use of reduced voltage starting. First, to reduce the high starting current drawn by the motor. Second, to reduce the starting torque provided by the motor. The simplicity, ruggedness, and reliability of the squirrel cage induction motors have made them the standard choice for alternating current, all-purpose, constant speed motor applications. Several types of motors are available. Therefore, various kinds of starting methods and control equipment are also obtainable. The motor, the revolving field. The squirrel cage motor consists of a frame, a stator, and a rotor. The stator or stationary portion carries the stator windings. The rotor is a rotating membrane, which is constructed of steel laminations mounted rigidly on the motor shaft. The rotor windings consist of many copper or aluminum bars fitted into slots in the rotor. The bars are then connected at each end by closed continuous rings. The assembly of the rotor bars and end rings resembles a squirrel cage. This similarity gives the motor its name, squirrel cage motor. For a three-phase motor, the stator frame has 3 windings. The stator for a squirrel cage motor has never fewer than 2 poles. The stator windings are connected to the power source. When a 60 Hz current flows in the stator winding, a magnetic field is produced. Because of the 3-phase alternating current and the displacement of each phase winding, this field circles the rotor at a speed equal to the number of revolutions per minute, or RPM, divided by the number of pairs of stator poles. Therefore, on a 60 Hz, a motor having one pair of 2 poles will run at 3600 RPM. A 4-pole motor, 2 pairs of 2 poles each, will run at 1800 RPM. The revolving stator magnetic field induces current in the short-circuited rotor bars. The induced current in the squirrel cage then has a magnetic field of its own. The two fields interact, with the rotor field following the stator rotating field, thereby establishing a torque on the motor shaft. The current induced has its largest value when the rotor is at a standstill. The current then decreases as the motor comes up to speed. In designing motors for specific applications, changing the resistance and reactance of the rotor will alter the characteristics of the motor. For any one rotor design, however, the characteristics are fixed. There are no external connections to the rotor. In the next image, you can see an assembly of a squirrel cage motor. Lock rotor currents. The lock rotor current and the resulting torque are factors which determine if the motor can be connected across the line or if the current must be reduced to obtain the required performance. Lock rotor currents for different motor types vary from 2.5 to 10 times the full load current of the motor. Some motors, however, have even higher inrush current. The induction motor at start. Please see the next image for the behavior of the current taken by an induction motor at various speeds. First, note that the starting current is high compared to the running current. In addition, the starting current remains fairly constant at a high value as the rotor speed increases. The current then drops sharply as the motor approaches its full rated speed. Since the motor heating rate is a function of 1 squared times R, or copper loss, this rate is high during acceleration for most of the acceleration period. The motor can be considered to be in the locked condition. No low rotor speed. The induced current in the rotor gives rise to magnetic forces which cause the rotor to turn in the direction of rotation of the stator field. The motor accelerates until the necessary speed is reached to overcome windage and friction losses. This speed is referred to as the no-load speed. The motor never reaches synchronous speed since a current will not be induced in the rotor under these conditions, and thus the motor will not produce a torque. Torque refers to the twisting or turning of the motor shaft. The motor bars of a squirrel cage must be cut by the rotating magnetic field to produce a torque. Speed under load. As the rotor slows down under the load, the speed adjusts itself to the point where the forces exerted by the magnetic field on the rotor are sufficient to overcome the torque required by the load. Slip is the term given to the difference between the speed of the magnetic field and the speed of the rotor. The slip necessary to carry the full load depends on the characteristics of the motor. In general, the following situations are true. The higher the inrush current, the lower the slip at which the motor can carry the full load, and the higher the efficiency. Second, the lower the value of inrush current, the higher the slip at which the motor can carry the full load, and the lower the efficiency. An increase in the line voltage causes a decrease in the slip, and a decrease in the line voltage causes an increase in the slip. In either case, sufficient current is induced in the rotor to carry the load. A decrease in the line voltage causes an increase in the heating of the motor. An increase in the line voltage decreases the heating. In other words, the motor can carry a larger load. The slip at rated load may vary from 3% to 20% for different type of motors. Variation of torque requirements. Different loads have different torque requirements. This must be kept in mind when considering the starting torque required at the rate of acceleration most desirable for the load. In general, a number of motors will satisfy the load requirements of an installation under normal running conditions. However, it might be more difficult to use a motor that will perform satisfactorily during both starting and running. Often, it is necessary to decide which is the most important factor to consider for a particular application. For example, a motor may be selected to give the best starting performance, but there may be a sacrifice in the running efficiency. In another case, to retain a high running efficiency, it might be necessary to use a motor with a high current inrush. For this and other examples, the selection of the proper starter to overcome the objectionable features is an important consideration in view of the high cost of energy today. The machine to which the motor is connected, it might be started at no load, normal load, or overload conditions. Many industrial applications require that the machine be started when it is not loaded. Thus, the only torque required is that necessary to overcome the inertia of the machine. Controlling torque. The most common method of starting a polyphase squirrel cage induction motor is to connect the motor directly to the plant distribution system at full low voltage. In this case, a manual or magnetic starter is used. From the standpoint of the motor itself, it is perfectly acceptable practice. As a matter of fact, it is probably the most desirable method of starting this type of motor. Overload protective devices have reached such a degree of reliability that the motor is given every opportunity to make a safe start. The application of a reduced voltage to a motor in an attempt to prevent overheating during acceleration is generally wasted effort. The acceleration time will increase and correctly sized overload elements may still trip. Reduced voltage starting minimizes the shock on the driven machine by reducing the starting torque of the motor. A high torque applied suddenly with full voltage starting may cause belts to slip and wear, or may damage gears, chains, or couplings. The material being processed or conveyed may be damaged by the suddenly applied jerk of high torque. By reducing the starting voltage or current at the motor terminals, starting torque is decreased. Reduced voltage, reduced current, and reduced torque. The category of reduced voltage methods generally includes all the starting methods which deviate from the standard line voltage starting. Not all of the starting schemes reduce the voltage at the motor terminals, Even reduced voltage starters reduce the voltage only to achieve either the reduction of the line current or the reduction of the starting torque. The reduction of the line current is the most commonly desired result. You should note one important point. When the voltage is reduced to starting motor, the current is also reduced, and so is the torque that the machine can deliver. Regardless of the desired result, either reduced current or reduced torque, remember that the other will always follow. If this fact is kept in mind, it is apparent that the motor which will not start at load at full voltage cannot start the same load at reduced voltage or reduced current conditions. Any attempt to use a reduced voltage or reduced current will not be successful in accelerating troublesome loads. The very process of reducing the voltage and current will further reduce the available starting torque. Need for reduced current starting. The most common function of reduced voltage starting device is to reduce or in some way modify the starting current of an induction motor. In other words, the rate of change of the starting current is confined to prescribed limits, or there is a predetermined current time picture that the motor presents to the supply wiring network. A current time picture for an entire area is maintained and regulated by the public power utilities serving the area. The power company attempts to maintain a reasonable constant voltage at the points of supply so that the lamp flicker will not be noticeable. The success of the power company in this attempt depends on the generating capacity to the area, transformer and line loading condition and adequacies, and the automatic voltage regulating equipment in use. Voltage regulation also depends on the sudden demands imposed on the supply facilities by residential, commercial, and industrial customers. Transient overloading of the power supply may be caused by, first, sudden high surges of reactive current from large motors on starting. 2. Pulsations and current taken by electrical machinery driving reciprocating compressors and similar machinery. 3. The impulse demands of industrial X-ray machine equipment. And 4. The variable power factor of electric furnaces. All of these demands are capable of producing voltage fluctuations. Therefore, each of these particularly difficult loads is regulated in some way by the power utility. The utility requires the use of some form of reduced voltage, reduced current method, and it helps its customers determine the best method. Power company rules and regulations vary between individual companies and the areas served. The following list gives the most commonly applied regulations. All of the possible restrictions of energy usage are not given. An installation may be governed by just one of these restrictions, or two or more rules may be combined. Some of the regulations include a maximum number of starting amps either per horsepower or per motor. 2. A maximum horsepower for line starting. A limit in percentage of full load current is set for anything above this value. 3. A maximum current in amps for a particular feeder size. It is up to the user to determine if the motor will conform to the power company requirements. 4. A maximum rate of change of line current taken by the motor. For example, 200 amps per half second. It should be apparent that it is very important that the electrician must understand the behavior of an induction motor during the startup and acceleration periods. Such an understanding enables you to select the proper starting method to conform to local power company regulations. Although several starting methods may appear to be appropriate, a careful examination of the specific application will usually indicate the one best method for motor starting. Typical starting methods. Starting methods for polyphase motors. The most common methods for starting polyphase squirrel cage motors include the full voltage starting, a hand-operated or automatic starting switch throws the motor directly across the line. Next, primary resistance starting. A resistance unit connected in series with a stator reduces starting current. Next is auto transformer or compensator starting. Manual or automatic switching between the taps of the auto transformer gives reduced voltage starting. Next, impedance starting. Reactors are used in series with the motor. Next is start delta starting. The stator of the motor is start connected for starting and the delta connected for running. Next is part winding starting. Stator windings of the motor are made up of two or more circuits. The individual circuits are connected to the line in series for starting and in parallel for normal operation. Of these methods, the two most fundamental ways of starting squirrel cage motors are full voltage starting and reduced voltage starting. Once again, full voltage starting can be used where the driven node can stand the shock of starting and objectionable line disturbances are not created. Reduced voltage starting may be required if the starting torque must be applied gradually or if the starting current produces objectionable line disturbances. Starting methods for single-phase motors. Starting methods for single-phase motors involve disconnecting the start winding of a split-phase motor when the motor reaches about 75% of its rated speed, as opposed to how the motor is connected to the power line. Single-phase motors are small horsepower and almost all are started across the line. There are several different types of single-phase motors. The motors described in this video are the split-phase type. Split-phase motors derive their name from the manner in which they produce a rotating magnetic field and the stator winding. A rotating magnetic field is used to start the rotor turning and cannot be produced with a single phase. At least two phases must be present to produce a rotating field. Split-phase motors simulate the current of a two-phase system, which are 90-degree out of phase with each other. This is accomplished by placing two separate windings in the core of the stator 90 degrees apart. Please see the next image. The run winding is made of a larger wire and is placed deeper in the slots of the core material. The start winding is made with a smaller wire and placed near the top of the slots in the core material. The run windings, therefore, has less resistance and more inductance than the start winding. When the motor started, these two windings are connected in parallel. Since the run winding has more inductive reactance and less resistance than the start winding, the current flow through the run windings lags the voltage more than the current flow through the start winding, producing an out-of-phase condition for these two currents. It is this out-of-phase condition that produces the rotating magnetic field. This type of split-phase motor is called a resistant start motor. It produces a phase angle of about 35 to 40 degrees between the current in the run windings and the current in the start winding. Although this phase angle is not 90 degrees, it is enough to produce a rotating magnetic field to start the motor. When the motor reaches about 75% of the rated speed, the start winding is disconnected and the motor continues to operate with only the run winding energized. Although the resistant start motor will start with only a 35-degree to 45-degree phase shift between the run winding current and start winding current, it produces a weak starting torque. Maximum starting torque is obtained when the run winding and start winding currents are 90 degrees out of phase with each other. Some motors accomplish this by inserting an AC electrolytic capacitor in series with the start winding. The capacity of reactance of the capacitor causes the start winding current to lead the voltage and produce a 90-degree phase shift between the run winding current and start winding current. Regardless of which method is used to produce the rotating magnetic field, the start winding of either motor must be disconnected from the power line when the rotor reaches about 75% of the rated speed. Failure to do so will result in damage to the start winding. Centrifugal switch. Split-phase motors intended to operate in the open accomplish this by the use of a centrifugal switch connected to the shaft of the rotor. The centrifugal switch is operated by spring-loaded counterweights. When the rotor reaches a certain speed, the counterweights overcome the springs and open the switch, disconnecting the starting winding from the power line. Hot wire starting relay. Centrifugal switches cannot be used on all types of split-phase motors. However, hermetically sealed motors used in refrigeration and air conditioning or submerged pump motors must use some other means to disconnect the start winding. Although the hot wire relay is seldom used anymore, It is found on some older units that are still in service. The hot wire relay function as both a starting relay and an overload relay. In the next image, it is assumed that a thermostat controls the operation of the motor. When the thermostat closes, current flows through a resistor wire in two normally closed contacts connected to the start and run windings of the motor. The starting current of the motor is high, which rapidly heats the resistant wire, causing it to expand. The expansion of the wire causes the spring-loaded start winding contact to open and disconnect the start winding from the circuit, reducing motor current. If the motor is not overloaded, the resistant wire never becomes hot enough to cause the overload contact to open, and the motor continues to run. If the motor should become overloaded, however, the resistant wire will expand enough to open the overload contacts and disconnect the motor from that line. Current relay. The current relay operates by sensing the amount of current flow in the circuit. This type of relay operates on the principle of a magnetic field instead of expanding metal. The current relay contains a coil with a few turns of a large wire and a set of normally open contacts. The coil of the relay is connected in series with the run winding of the motor, and the contacts are connected in series with the starter winding. When the thermostat contact closes, power is applied to the run winding of the motor. Since the start winding is open, the motor cannot start. This causes a high current flow in the run winding circuit. This high current flow produces a strong magnetic field in the coil of the relay, causing the normally open contacts to close and connect the start winding to the circuit. When the motor starts, the run winding current is greatly reduced, allowing the start contacts to reopen and disconnect the start winding from the circuit. Solid state relay starting. The solid state relay starting is rapidly replacing the current starting relay. The solid state relay uses a solid state component called a thermistor, and therefore has no moving parts or contacts to wear or burn. A thermistor exhibits a rapid change of resistance when the temperature reaches a certain point. This particular thermistor has a positive coefficient of resistance, which means that it increases its resistance with an increase of temperature. The next image illustrates the connection for a solid state relay. When power is first applied to the circuit, the resistance of the thermistor is relatively low, 3 or maybe 4 ohms, and current flows to both the run and start windings. As current flows through the thermistor, its temperature increases. When the temperature becomes high enough, the thermistor suddenly changes from a low resistance to a high resistance, reducing the start winding current to approximately 30 to 50 milliamps. This has the effect of disconnecting the start winding from the circuit. Although a small amount of leakage current continues to flow, it has no effect on the operation of the motor. This leakage current maintains the temperature of the thermistor and prevents it from returning to a low resistance while the motor is in operation. When the motor is stopped, a cool down period of about 2 to 3 minutes should be allowed to allow the thermistor to return to a low resistance. Potential starting relay. The potential starter relay is used with a different type of split phase motor called the capacitor start, capacitor run, or permanent split capacitor motor. This type of split phase motor does not disconnect the starting winding from the circuit. Since the start winding remains energized, it operates very similarly to a true two-phase motor. All of these motors contain a run capacitor that remains connected in the start winding circuit at all times. Many of these motors contain a second capacitor that is used during the starting period only. This capacitor must be disconnected from the circuit when the motor reaches about 75% of the rated speed. Open case motors generally use a centrifugal switch to perform this function. But hermetically sealed motors generally depend on a potential starting relay. The potential relay operates by sensing the increase of voltage induced in the start winding when the motor is in operation. The coil of the relay is connected in parallel with the start winding of the motor. A normally closed-end start contact is connected in series with the starting capacitor. When the power is connected to the motor, both the run and start windings are energized. At this time, both the run and start capacitors are connected in the start winding circuit. The rotating magnetic field of the stator induces a turn in the rotor of the motor. As the rotor begins to turn, its magnetic field induces a voltage into the start winding, increasing the total voltage across the winding. Since the coil of the potential relay is connected in parallel with the start windings, this voltage increase is applied to it also, causing the normally closed contact connected in series with the starting capacitor to open and disconnect the starting capacitor from the circuit. Okay, folks, that is it for today. Again, thank you so much for joining me. Please like, share, subscribe, and feel free to comment and send me any message or any questions you might have. Thank you and see you in the next one.